Okay, now we move on to natural deduction with quantifiers. So we're going to talk about only the for all rules for the moment. So the two for all rules are for all introduction and for all elimination. For all elimination is pretty straightforward. If you have that for all choices of x, p of x is true, then p of a is true for any variable a. Sure, that makes sense. If it's true for everybody, then it's true for any choice of person. For all introduction is a little bit trickier. If you know that p of a is true where a represents an arbitrary person, then you can show for all x, p of x. So I like to think of this rule as going backwards. So whenever I'm trying to prove for all x, p of x, what I like to do is create a new variable, and so that's a variable that doesn't show up anywhere else in the proof. I'll call that variable a. And I have to try and show that p of a is true, p is true for this value a. Okay? If you can get to this stage here, then you can use for all introduction to jump down. And by working backwards, you won't get caught in silly little traps where you accidentally pull the thing beyond the guard of the variable and so on. So let's go through an example. Let's try to prove this statement here. For all x, p of x and q of x means for all y, p of y, and separately for all z, q of z. So this makes sense. If everyone in the world wears red shirts and blue pants, then everyone in the world wears red shirts, and also separately, everyone in the world wears blue pants. So let's prove it. So we're at the thing that we're given at the top, and I'm at the thing I want at the bottom. For all y, p of y, and for all z, q of z. Okay? So the only way I can prove this statement here is if this side were true and that side were true. Because there's no way to work backwards because we don't have a for all on the bottom by itself. So we can sort of work backwards on the and. So I have like two things I need to obtain. I need to obtain for all y, p of y. And how am I going to do that? Well, this is where we can use for all introduction backwards. If I want to be able to prove for all y, p of y, I should be able to show p of a for an arbitrary choice of a. So I can write my arbitrary choice of a here. No, at the top. It is somehow get p of a. Similarly, I need to obtain for all z, q of z. So I'm just going to squeeze that in because I've left myself enough room. For all z, q of z. And the only way I can obtain this statement is if I can show q of a for an arbitrary a. Okay? At this point, we can use for all elimination forward on this rule here. So I have for all x, p of x, and q of x. So certainly this is true for any choice of x. I'm going to choose a. So we have p of a and q of a by for all elimination. And then I can use and elimination to break this up into the two parts, p of a and q of a. And hence the proof follows. So we can put in our line numbers. Always leave yourself lots of room so you have to sort of squish that line in. So that's why I like to write nice and big and leave big gaps. So this was given. This is for all elimination line 1, and elimination line 2, and elimination line 2. Here, because there's no constraints on a, this is an arbitrary a, we have for all z, q of z, because I've got q of a for an arbitrary a. So, and introduction line 3. Similarly, for all y, p of y, I can use and introduction on line 4. I've got for all z, q of z, I've got for all y, p of y, therefore both of them together with a logical and is true. By and introduction, lines 6 and 5. Okay, there we go. As an exercise, you should try and prove that if you do for alls in a different order, it doesn't matter. So try to prove, if you know that for all x and for all y, p of xy, then you can conclude for all y, for all x, p of xy. So have a go at that.